Breakthroughs in quantum science are rewriting the rules of technology. But one of the biggest puzzles remains. How do we actually store and control quantum information long enough to make true quantum computing possible? Enter the debate over mechanical quantum memories for microwave photons, a topic that's stirring excitement and controversy in equal measure. A mechanical quantum memory refers to a device that can reliably capture, store, and later retrieve quantum data carried by microwave photons, using the vibrations of a tiny mechanical object as the storage medium. The stakes are high. Reliable quantum memories are central to the future of quantum networking, error correction, and ultimately scalable quantum computers. But here's where it gets controversial. Can mechanical systems really outperform existing approaches in terms of coherence, noise, and integration? To set the scene, Wahlquist et al. in 2009 highlighted the promise of hybrid quantum devices, bringing together different physical systems to exploit their best features. This sets the foundation for the field, building devices that marry the strengths of, for instance, superconducting qubits, the leading light in quantum processors, with mechanical resonators, potentially yielding unprecedented control over quantum states. Koritsky et al., 2015. Over the past decade, circuit quantum electrodynamics has revolutionized our ability to manipulate single photons and qubits on a chip. Researchers such as Clerk et al., 2020, and Kjaegaard et al., 2020, laid out the advances in superconducting circuits, while De Leon et al., 2021, discussed the profound materials challenges that still hamper quantum hardware today. Think defect-induced noise or energy loss that limits memory lifetimes. One classic example, the quest to reduce energy loss in nanomechanical resonators, so quantum signals can be stored nearly indefinitely. Galliou et al., 2013, Engelson et al., 2024. Could these ultra-low loss devices finally crack the problem? But, and this is the part most people miss, recent breakthroughs in nanomechanical resonator technology have pushed phonon, mechanical quantum excitation, lifetimes to record levels. McCabe et al., 2020, for example, demonstrated nanoacoustic resonators with phonon lifetimes long enough to open the door to quantum memories that compete directly with or even surpass their electromagnetic rivals. That's a bold claim. At the same time, groups are experimenting with nonlinearities and exotic states, like the mechanical Schrödinger cat states, in devices weighed in micrograms. Bild et al., 2023. Here's where opinions sharply divide. Are these mechanical quantum memories genuinely scalable and robust, or does their complexity introduce new and potentially fatal sources of error? Chamberlain et al., 2022, explored pathways to fault-tolerant computation using clever coding strategies. But even the fiercest supporters admit that mechanical memories bring their own challenges in terms of fabrication and integration with superconducting circuits. Petchel et al., 2018, Chu and Groblacher, 2020. Hybrid systems involving mechanical, electromagnetic, and even optical elements are now at the heart of quantum information research. Pioneering demonstrations have achieved feats like transferring quantum states via phonons, Bienfait et al., 2019, squeezing the energy uncertainty in massive oscillators, Ma et al., 2021, and entangling distant qubits using mechanical links, Cleland et al., 2024. Sound far-fetched? Just a few years ago, so did controlling mechanical oscillators at the level of single quanta, O'Connell et al., 2010. And yet, beneath the optimism, serious skeptics remain. Is it really possible to mass-produce high-coherence mechanical devices? Can we ever fully eliminate the noise that plagues solid-state systems, given the persistent presence of two-level system defects in common substrate materials? Phillips, 1987. Lissenfeld et al., 2019. What's more, as integration efforts scale up, will new forms of decoherence emerge that we haven't even considered? As quantum engineers push the boundaries, the mechanical quantum memory debate is far from settled. Will mechanical systems become the backbone of tomorrow's quantum information networks? or remain a fascinating niche outpaced by yet another breakthrough in photon-based or purely superconducting approaches? What do you think? Is mechanical quantum memory a genuine pathway to scalable quantum computing, or are its challenges simply too great to overcome? Which emerging approach excites you most, and where do you see the hottest debates playing out? Let us know in the comments below. Agreement and dissent are equally welcome.